Have you ever wondered why the food turned golden brown when cooked and looks incredibly delicious, while the sliced apple turned brown and looks unappealing? Well, the secret lies in the chemical and enzymatic reactions, which we often called as a browning reaction. So let's unravel the mysteries behind this phenomena. Welcome to Food Catalyst, and this is Venkadesh. So browning reaction. So this reaction is very much important for most of the food technology related exam questions. So what is a browning? Browning is a common color change which we seen during the preparation, processing and storage. So the color can be changed from cream or pale yellow to all the way to brown or black. Okay, and see, coconut has a special ability. It can develop a saffron color while browning. Okay, see, this browning can be desirable or undesirable. In such cases where it is desirable, this is highly associated with the quality of the products. For example, the brown color and the flavor which is developed in baked goods, potato chips, roasted nuts and coffee beans and other processed food, which is highly desirable, right? The color of the brown colors and the flavors which is developed during the browning. But in certain cases, this will give off color, off odor and off flavors. Okay, the flavor can be changed from stale to very bitter. Okay, this you can see in the milk, egg, dry fruits, cut fruits and citrus fruit juice concentrate, canned milk and coconut. So this browning is very much mysterious, that it can be desirable or it can be undesirable. So let's discuss what is this phenomenon. So browning can be divided into two types of reactions: non-oxidative browning, oxidative browning. Okay, so non-oxidative browning and oxidative browning. In case of oxidative browning, we have two important browning reactions. One is enzymatic browning, then ascorbic acid oxidation browning. Okay, there is a third type of oxidative browning also. It's called lipid oxidation browning. Lipid oxidation browning. Okay, this is a third type, which is not that important in exam perspective, but that is also a kind of oxidative browning. In case of non-oxidative browning, we have the legend, which we can say that two important reactions in the food processing, which is caramelization and Maillard reaction. These two reactions is ruling majority of the confectionery products. Okay, so let's discuss this non-oxidative reactions first. See, non-oxidative reactions, or we can say non-enzymatic browning. So here the enzyme is not involved. Okay, so these reactions are mainly responsible for the color and flavor of foods such as dates, honey and chocolates. Okay, so the foods which is like the dates, honey and chocolate, the color and flavor are developed due to non-oxidative. So here there is a presence of reducing sugars. Okay, so the reducing sugars present in the dates, honeys and chocolates, which is responsible for the non-oxidative browning. On heating, this will undergo ring opening, enolization, dehydration and fragmentation. Don't need to worry about what is ring opening, enolization, which we will discuss that later on. But this reducing sugar is going to undergo series of reactions. Okay, and ultimately it will give a unsaturated carbonyl compound. This unsaturated carbonyl compound is the responsible compound, which is actually a polymer. Okay, because it will condense at the end. So the reducing sugar will condense. First of all, it will be a mono or disaccharide, then it will combine and form a oligosaccharide, then polysaccharide, then finally the huge polymers. That polymer is unsaturated carbonyl compounds. It will produce the colors and flavors. Okay, so don't need to worry about it. I'll explain it in detail. And the heat induced reactions occurs in two ways. One is a caramelization and Maillard reaction. So the difference between these two is important. First, let me explain what are these two reactions. Okay, So let's start with the caramelization. So caramelization means, let's simply see this point. See, sugar, take a sugar which is either dry or syrup format, heat the sugar under a catalyst. This sugar will undergo number of reactions, okay, and this will lead to two things. First one is, it will create a equilibrium between the anomeric and the ring forms. So if you don't know what is anomeric carbon and what is a ring form of glucose, then go and watch the carbohydrate video. Okay, go and watch the carbohydrate video, so which we have uploaded in the channel. So this specific phenomena will be explained in the video. Okay, next is inversion of sucrose, condensation and polymerization. This is what I told you. Inversion of sucrose will happen, condensation will happen, polymerization will happen. So all the monos and disaccharides will converted into oligosaccharides and polysaccharides, and that oligosaccharides and polysaccharides will undergo several reactions like isomerization, okay, dehydration and fragmentation. Finally it's end up as a saturated polymers or saturated carbonyl compounds. This compound has a brown in color. See why it is in brown color, right? So it can be any color. Why brown color? See, this brown color is due to the double bonds which are introduced in the sugars. Okay, see, in case of furan and unsaturated polymer, it will form a conjugated double bonds. Okay, you know what is furan, right? I have explained in the carbohydrate video. See, this furan or unsaturated polymers will form a conjugated double bonds. That bonds will absorb the light and it will produce a color brown. Okay, so that's how the brown color is formed, and the reason behind the brown color is a double bond. Okay, so with the proper use of catalyst, it would be possible to conduct a caramelization to provide either flavoring or coloring caramel for the use of food. Okay, so that's it. So let's get into the reaction. Caramelization. This caramelization reaction can be either used for flavoring or used for coloring. Okay, so let's take an example of coloring first. See, in case of coloring, we have to take the glucose syrup or any syrup which we have to heat it. Okay, which we have to heat the compound along with the acid or base. Why? Because see, by introducing either acidic environment or a basic environment, we can increase the process of caramelization. Okay, so that's why we are introducing the disulfuric acid and then ammonia. See, here it is the diluted sulfuric acid, because we are adding ammonia to saturate a little bit. Instead of using concentrated sulfuric acid, we are using diluted sulfuric acid and ammonia, and this will give us the caramel colors. Okay, so there are three types of caramel colors. The first type is called as acid fast caramel. Okay, acid fast caramel. This is the most used caramel. The only one thing which you need to take care of is the catalyst which you are using here is ammonium bisulfate catalyst. So this caramel will ultimately give you the cola color. The color which you are seeing in the cola, which is actually come from the acid fast caramel. Okay, next one is brewer's color beer. So the color which you are seeing in the beer is actually come from this method, where the sucrose is added with ammonia. Okay, so finally baker's color. So the baker's color is nothing but the sugar is undergoing a process called pyrolysis. Okay, sucrose is undergoing the process called pyrolysis. So that's how we are getting a baker's color. We are not adding anything like so fancy. Just the reaction of pyrolysis itself is enough. So what is a pyrolysis then? Pyrolysis is a thermochemical process that breaks down the complex material into smaller and volatile fragments. Okay, so it's a thermochemical process which simply break down the components. So it will break down the sucrose and it will give the color of brown color. Okay, now let's come back to the flavoring. See, for flavoring, we have to take the sucrose, concentrated syrup, and we have to heat the sucrose to get the caramel flavor. See, here also we can use the sucrose and do the pyrolysis, and we can get an unsaturated ring. See, this ring can be either maltar or isomaltar, which is responsible for the flavors in bread. Okay, the usual maltar flavor which you are like experiencing in the bread is actually come from the sucrose pyrolysis. Okay, that's how we'll get the flavors from the caramel. Okay, so the caramelization temperature is different for different sugars. Okay, so for fructose it's the least, which is 110, followed by galactose, glucose and sucrose, all is 160 degrees Celsius, and then finally maltose is 180. So which is the most resistant sugar for caramelization temperature within this option is maltose, and the least resistant is fructose. Okay, so let's move on. After this point, we need to know, as I told you before, the rate of the caramelization is generally slowest at the pH of 7. If you want to accelerate it, what you have to do, either you have to get into an acidic environment which is below 3, or basic environment which is below 9. Simple, right? So that's why we are adding acid and base. Done, that's it. Okay, so either by introducing an acidic environment or a basic environment, we can increase the process, we can accelerate the process. So the next is Maillard reaction. Okay, so Maillard reaction is basically a different version of let's say this caramelization reaction. Let me explain why. So take an example of dates, honey or chocolate. All these have a reducing sugars, right? This reducing, there we are only using the reducing sugar, we are not using anything else. But here we are also using sugars along with amino acids. Sugars along with the amino acids. See, what is reducing sugar? First of all, reducing sugar is something which has a hemiacetal ring. Okay, if something has a hemiacetal ring, then that is a reducing sugar, because in that ring we can easily able to reduce the sugar in that format. So that's why we have a like reducing sugar as a reducing sugar which is named as a reducing sugar, because it has a hemiacetal ring. I have explained the hemiacetal ring also in the previous video. So the first reaction in the Maillard reaction is to open this ring. Okay, so ring opening and dehydration is the first step. So once you have opened the ring, the next step is enolization. See, enolization is sugar reordering. For example, it will reorder the sugar in such a case, like it will reorder the H and O, and the oxygen will bond with H and C, right? Either it can bond with H, which is hydrogen, C, which is carbon. So by reordering this format, it can able to convert, this is an important point, the enolization is a reaction which can able to convert the aldose into a ketose. So that's why it's called a sugar reordering. Okay, first we open up the ring, next we are doing the reordering. Third one is dehydration, removing some water, then fragmentation, we are splitting up, then condensation. Finally we'll get the unsaturated carbonyl compound, which has flavors and colors. So this you might have seen, this is almost similar to the previous ones, but here the difference is, here the amino acids are involved. Okay, so let's see. Maillard reaction is usually a complex group of many reactions. The carbonyl group of sugar, which is can be either aldehyde or ketone in a reducing sugar, it's combined with the basic amino groups of protein, peptides and amino acid and produce sugar amines. This sugar amines form a brown color at lower temperature than that of the formation of the caramelization. For example, what they are telling is, if you want to get a brown color quicker with low temperature, you have to follow the Maillard reaction rather than the caramelization reaction, because the Maillard reaction with less temperature you can easily get the sugar, usually get the brown color. Okay, the sugar amines form a brown color at a lower temperature than that of the formation of the color by caramelization. Okay, so which is the most efficient way to make a brown color? Then that means it is Maillard reaction, because the temperature which you are giving is very much lesser in the Maillard reaction, which is higher in the caramelization. That's it. So that's why the browned food predominant reaction products are Maillard reactions. See, in most of the browned products which you are like seeing like caramel or cola or something, most of the time they will follow the reaction of Maillard rather the caramelization. Okay. Now I am taking this exact reactions which I have mentioned. Now I am splitting into a different compound and I am going to explain it. Okay. See, as I told you, I am taking sugar. It's either aldehyde or ketone, and I am adding with the amino acids. Okay, and I am going to heat the mixture. And what is the first step? As I told you, ring opening. So once it open a ring, it will form a new ring. The ring is glycosylamine. Okay, this glycosylamine is also called as shift base. It's also called as shift base. So the next step of the glycosylamine is a enolization. We are like reordering the glycosylamine to convert it from, if it is either a aldehyde or ketone, we are converting it into the another format. If it is an aldehyde, we will convert it into ketone. If it is a ketone, we will convert it into aldehyde. This product is called as Amadori product. Whatever the product which we are getting using the enolization, that product is called as the Amadori product. Okay, so next step is obviously dehydration and fragmentation. So the products like hydroxymethyl furfural, pyroaldehyde, it can be formed during this process, dehydration and fragmentation, and this product will finally give us the melanoids. Okay, so this is a condensation reaction. Okay, the melanoids which we are producing during this reaction is a condensation reaction. So that is responsible for either the aroma or the brown color. Okay, so that's it. This is the simplest explanation of what is going to happen in the Maillard reaction. Now let's split into further. Let's start with each and every process. The first step. So this is the step 1. So the first step of the process. So we are taking a glucopyranose. So this is an aldose. It's not a ketose. So you can take either D-glucopyranose or D-fructofuranose, whatever it is, and we are opening the ring. Okay, here is an important part. We are opening the ring and we are adding the, we are opening the ring and we are nucleophilic attacking with the amino nitrogen. So what happens is nitrogen has been infused into the glucopyranose and now it is called as glycosylamine. So the carbonyl compound of the reducing sugar in the open chain form first undergoes a nucleophilic attack. Okay, so first undergoes a nucleophilic attack by the amino nitrogen lone pair of the electron. By the amino nitrogen lone pair of the electron. So that's the first step. Carbonyl compound reacting with the amino nitrogen through a nucleophilic attack, and this is followed by the dehydration. Okay, that is okay. Ultimately we'll get a compound called as glycosylamine. Now let's go to the second step 2. This is the step 2. Step 2 is rearrangement of glycosylamine. See, glycosylamine is an aldose. After enolization, it is converted into 1-amino 2-keto sugar. Okay, 1-amino 2-keto sugar. This rearrangement is called as Amadori rearrangement. So this rearrangement of glycosamine into the 1-amino 2-keto sugar is called as Amadori rearrangement. For example, if you are taking ketos, it's not glycosylamine. In ketos also it's same glycosylamine only. This step is same for both the compound. This glycosylamine formation is same for either if you are using aldose or ketose, it is same. But if you are produced using ketose, then it will produce the 2 amino aldose. If you are produced using aldose, it will produce 1 amino 2 ketose. Okay, this reverse process converting from ketose to aldose is called as reverse amidori. Simple, right? Or another name is Heinz rearrangement. So see, we have seen two things. One is we have seen how we have to form how we are doing the ring opening and make the glycosylamine. Once we have opened the ring, we are rearranging the products. Okay, we are rearranging the products in the glycosylamine. If it is an aldose, we are converting into ketose. If it is a ketose, we are converting into aldose. That's it. Okay, so this is the first 2 steps. Third step, decomposition. Okay, decomposition of the amidori compounds to produce the melatonin pigments. Okay, so this amidori products, it can be go into 2 ways. Okay, the first way is producing 3-deoxyhexone. So in this way, it can make furanaldehyde. Okay, in this way, 3-deoxyhexanose can produce the 5-hydroxymethylfuranaldehyde, and ultimately it will give us the melanoidin pigments. Okay, this melanoidin pigments have pyrazine or imisotyl rings. That is not necessary, but you should know there are 2 ways to reach the melanoidin pigments. One way is through the 3-deoxyhexone, and the another way is called as methyl alpha dicarbonyl compound. Okay, alpha dicarbonyl compound. So this step is an intermediate step. Then it will further produce reductans, and reductans will produce melanoidin pigments. Or it can directly produce, instead of producing the furanaldehyde or reductans, it can directly produce the melanoidin pigments. So this is the last step of how it is decomposed and finally reaching the pigments called as melanoidin pigments. Okay, that you need to note one thing. See, the loss of essential amino acids like lysine, arginine, histidine is inevitable, right? Because obviously you are using the amino acid. You are using the amino acid in the first place. So there is a loss which is happening here. So the loss is inevitable. Okay, if you are doing this reaction, then you can expect a loss of essential amino acids, lysine, arginine, or histidine. But see, these are not the only pathways which leads to nutrient loss. Sometimes even if you this reaction doesn't mean that if you are going through any other pathways and getting the brown color, then we can able to say the this amino acids. No, it is not like that. There are some pathways like Strecker dehydration, which is way more nutrient loss than any other pathway. So the Strecker dehydration has the highest nutrition loss. Okay, so it can lose lot of nutrition. Okay, which means amino acids basically. See, let's see the Strecker dehydration. Okay, so the Strecker dehydration will follow this pathway. Take this alpha dicarbonyl compound, okay, this compound, and along with it will react with any other amino acids like valine, for example. Valine, okay. So the alpha dicarbonyl compound reacting with alpha amino acid, it will undergo decarboxylation, removing CO2, and it will produce tetramethylpyrazine and then aldehyde and then sugars, which is responsible for flavor and aroma, which we know. But this is the one which leads to lot of nutrition loss. A lot of amino acids has been used in this process. Okay, see, this is actually desirable in chocolate, honey, maple syrup and bread, because sometimes Strecker dehydration has to be used to make these products, chocolate, honey, maple syrup and bread. Okay, so is it desirable then? Not in all cases. Not in all cases the Strecker dehydration is desirable. Why? Sometimes it produces pre-melanoid compounds, which means before it attaining the melanoid pigments, it will stop the reaction because it will produce something called nitrosamine. What is nitrosamine? Which is a carcinogenic compound. It can cause cancer. So that's why all the Strecker dehydration reactions are desirable. In certain cases, it can produce the pre-melanoid compounds like nitrosamine. So we need to control that one. Okay, so how to control the non-oxidative browning? Simple. See, if you are giving a very low temperature, then we can control browning, right? Low temperature and isoelectric pH, which means, as we have seen before, if you are like maintaining the pH within 9, within 7, then the reaction will be much slower. So we can prevent a little bit of oxidative browning. Sorry, non-oxidative browning. Then you should have to keep either low moisture, which is 0%, or high moisture, which is 100%. Okay, if you are keeping it in between, if you are keeping it for 30% relative humidity, this is the relative humidity which you have to use to get the maximum of browning. If you want to achieve maximum browning, this might be a question. 30% relative humidity is the value which you have to follow. If you're keeping 0 or 100, non-oxidative browning will not happen. Even in strong acidic environment, protonation happens. So it will not start the first reaction. Glycosamine will not form. So the very first reaction will not happen if you are keeping it very strong. Okay. So it is very strong, not something like as I told you, 3 is the like good way to increase the speed of the reaction, right? But if you are going below 3, then the very strong reaction will make a protonation. So that's why it does not form the glycosamine. And we can also do a sulfide reaction. Okay, this sulfide reaction is the most famous reaction which we used to do. This will prevent the Maillard reaction. First of all, how? It will bond with amino acid. See, if it is bonding with amino acid, automatically the use of the reaction itself is invalid because the nutrient loss will be same. But we can prevent the colors. Okay, and see, in case of Strecker dehydration, it has no effect. It will prevent Maillard reaction, but it will not prevent the Strecker dehydration. So the sulfide doesn't have any effect in Strecker dehydration, but it has some effect in Maillard reaction. How? Because it will bond with the amino acid. Anyway, the nutrition loss will be the same, but it can prevent the color forming. Okay, that's it. We have completed the non-enzymatic browning. Now let's come to the enzymatic browning. So enzymatic browning, let me explain in the simplest way. See, in fruits and vegetables, we have phenols present inside. That phenols will be oxidized into orthoquinone. Okay, that phenols are oxidized into orthoquinone. How it is oxidized? By using an enzyme called phenolase. Okay, phenolase is an enzyme which will oxidize the phenols into orthoquinone. That orthoquinone will undergo polymerization and it will produce melanin. It's not melanoid, it's melanin. Yes, it is the same compound which is present all over us. Okay, which is protect us from the UV rays and all. See, this melanin is let's say it's a defense mechanism. Okay, it's a defense mechanism of the fruits and vegetables. Let me explain. See, enzymatic browning of fruits and vegetables is defined as a process where enzymes such as phenolase oxidize the phenols into orthoquinones, which is rapidly polymerized to form the undesirable black or brown pigments such as melanins. This process takes place in the presence of oxygen. That's why it's called as oxidative browning. Okay, see, this enzymatic browning becomes evident when fruits and vegetables are subjected to processing or mechanical injury. Okay, if you are cutting a slice of apple, then that slice of apple will be consider the fruit that consider that slice of apple as a damage to the tissue. So to prevent the damage, to cover the surface, it will start producing the melanin. Okay, so that's it. Simple reaction why the apples turn brown. This is the answer. Okay, it's a defense mechanism that the enzymes will do in order like that melanin will prevent from the outside environment to like influence further into the tissue. Okay, see, the phenolase is a group of enzyme. It's not just in one enzyme. It contains phenol oxide, cressolase, dope oxide, catecholase, and then polyphenol oxide, potato oxide, and then lacase, triosinase, sweet potato oxide, then grape peroxide, then phenolase complex. So see, in today's class we are going to see only the two important major reactions. Okay, two important. The first is hydroxylation A and oxidation B. Okay, hydroxylation A and oxidation B. Hydroxylation, it is actually involved two important enzymes which we have discussed above. One is phenol hydroxylase, first enzyme which is responsible for hydroxylation. Second enzyme which is responsible for the hydroxylation is cressolase. Okay, in case of oxidation we have polyphenol oxidase, which is the major reason for most of the enzymatic browning. Okay, because this enzyme is present in almost all the vegetables and fruits. So this is the major enzyme, polyphenol oxidase. It is here, PPO. This is a short form. Okay, and catecholase activity. So the oxidation responsible for for the oxidation reaction, there is two compound responsible. One is PPO and catecholase. In case of hydroxylation, we have two compounds. One is phenol hydroxylase and cressolase activity. Okay. See, this PPO, polyphenol oxidase, is a copper containing metalloprotein. Okay, it's a obviously it's a protein. All the enzymes are protein. It is a copper containing metalloprotein. You just need to know this because it is a very important component. They might ask this question. So this word is important. Copper containing metalloprotein. Okay, let me explain the reaction. So enzymes which is present in fruits such as apples, bananas, pears, gooseberry, kiwi, and vegetables such as lettuce, brinjal, all have this enzymes. Okay, whatever the enzyme which we have discussed, phenolase enzyme, it is present in all of these: apples, bananas, pears, gooseberry, and kiwi. Vegetables, it is lettuce, brinjal, mushrooms, asparagus, broccoli, carrot, and potato. Okay, so it can ultimately, as you can see in the images, it can ultimately turn the apple. Okay, it can ultimately, you can see this in this area, that it has started drowning and it started to heal itself. This is a process of, as I told you, it's a self-defense mechanism by the fruits. So it started to seal this place. Okay, so that's what the reaction is basically doing. Okay, now let's see this in a much deeper way. So as I told you, I am taking one example. Okay, so I am taking a phenolic compound as an example, and let me explain what will happen in this reaction. So I am taking triosine, a phenolic compound. Okay, and I am adding the oxygen and enzyme. Obviously the enzyme is present and the oxygen is also present. So first it will undergo hydroxylation reaction, as we have mentioned, the first reaction. That's why it's hydroxylation A. It will produce DOPA, dihydroxyphenylalanine. Okay, this DOPA is the first compound that it will produce. The second compound is oxidation reaction. So the second compound which is produced is dopaquinone. As we have discussed here, it will produce the quinone, orthoquinone, right? So that's how we are producing the dopaquinone. This combination of this hydroxylation plus oxidation reaction is the enzymatic reaction. So this reaction is the beginning step of the series of reactions you are going to see. Why we call this an enzymatic reaction? But this is a prior reaction which is going to happen. That's why it's an enzymatic reaction. So all the other reactions which you are going to see, it's a non-enzymatic reaction. Okay, so the next reaction is the dopaquinone will be producing the leuco compound. Leuco compound is a colorless compound. Further it will degrade to halochrome. which is a red color. Sometimes what will happen, this dopa will automatically produce the halochrome, okay, and that halochrome will produce the melanin at the end. Okay, so the step is, first of all, I am taking any one phenolic compound and I am doing the process of hydroxylation. It is producing dopa, and then after the oxidation it produces dopa quinone. Okay, this reaction is set of reaction is the enzymatic reaction. Then followed by non-enzymatic reaction. First it will produce leuco compound, which is colorless, then halochrome, which is a red color, followed by the melanin, which is a brown color compound, which we used to see in the apple. Okay, done. So this series of reactions, okay, this series of reaction is the enzymatic reactions. See how to control this reaction. See, to answer this question, we need to know what it needs to maintain the reaction. It needs oxygen, right? It needs oxygen, it needs enzyme, it needs a substrate. For example, it needs a phenol, right? And finally catalyst. By inhibiting any of these four components, we can control the reaction. Simple. Or changing conditions. One is the sulfate treatment or sulfite treatment, okay, which we have seen before, right? Sulfate treatment. So either by adding SO2 or pH less than 3, by making it by like adding any acetylants, okay, so the pH below 3 or lower. So by keeping it in an acidic condition, we can stop this reaction. Okay, so by changing the conditions and by like dipping it in the brine or syrup or any other thing. See, but the pH lowering by adding acetylants will also have another effect. That effect is called as chelating. See why? See, acetylants sometimes can act as a chelator, right? Chelator means it will go and bond with the copper. As we know that PPO has a copper containing metalloprotein. That's why it is important. See, it is a copper containing metalloprotein. This will form a complex. Okay, this will form a complex with the acetylants, and it will stop the reactions to happen. So by making a bond with the PPO. So that's why this acetylants is important. Okay, so that's it. That's how we have to control an enzymatic reaction. Simple. Then let's see like two other oxidative reactions. Both of these reactions are oxidative, which means it involves oxygen. So the first reaction is ascorbic acid browning. See, the ascorbic acid used as an agent to prevent the browning itself, right? Why we are using, you see, like here itself we have mentioned that pH 3 or lower by adding the acetylants. So then why it is inducing a browning, which means, see, we can use this to prevent the sliced fruits and vegetables, right? But this inhibitory effect is only temporary. Okay, because it can quickly consume during the redox process. After the redox process completion, it will started producing the brown pigments. Okay, this is mostly seen in the preserve, because in preserve we will add the citric acid or we will add the ascorbic acid, right? We mostly will add the lemons and then vinegars and kind of stuff. So that's why in the preserve we can easily see this phenomena like brown pigment acquiring phenomena. It's quickly done the redox process, and all the like acids will be like redoxed. Then the browning reactions will start to happen. That's why the ascorbic acid browning is an important browning. Lipid browning is, see, after the lipid has been oxidized, okay, after the lipid has been oxidized, the products of the oxidation along with the protein, amino acids and amines, it will produce a brown pigments. Okay, you can see this in the fatty fish. The fish has more pupa basically, right? So you can see this like if they are keeping the fatty fish in the frozen condition or something, you can see this phenomena like with the lipid browning phenomena, and also the fish which has high protein. Okay, the high protein fish is also affected because obviously not only the lipid oxidation products is involved, protein is also involved. So that also induces reaction. So that's it. That's the completion of browning. Okay, So let's try to answer the questions which is asked in the examination. First question. By which of the following process the fruit browning can be prevented by adding water? So this is a CFSO CBT2 examination question. Sterilization, dehydration, then live peeling, and then sulfate treatment. Sulfate treatment is the right answer. We have just seen this, right? Next question. Which of the following fruits is enzymatic browning observed? Lemon, grapes, pineapple, and apple. All these three has high acid, but apple is the right answer. I have also given some examples over there. Okay, so the answer is B. So next question. The Maillard browning, which is asked in the Gujarat FSO, okay, the Maillard browning is a result of interaction between what? Protein and a carbohydrate, right? So basically the NH2 of protein and CHO of carbohydrate will form an interaction. Okay, so the answer is B. Simple. Next question. Severe heat treating of surface layer of the food during the baking can cause Maillard browning reactions between sugar and amino acid. So they are talking about Maillard reactions and what happened Maillard reaction during baking. So first option is high temperature and low moisture content in the surface layer can also cause caramelization of sugar and oxidation of fatty acid to aldehyde, lactones, ketones, and esters. Second option is each amino acid produces a characteristic aroma when heated with a given sugar, owing to the production of specific aldehyde. Yes, both the option 1 and option 2 are right. Why? Because obviously high temperature and low moisture contents in the surface layer leads to caramelization. It will not lead to Maillard reaction, right? Because as we know how to control the Maillard reaction by keeping it in either low moisture content, right? 0 to either 0 or 100. So that's why it will undergo caramelization instead of Maillard reaction. Option 2 is obviously different aroma will be produced. We have seen few options also, right? Different types of aromas and flavors and etc. So that's why both the options are right. Final question. Brownish red color and altered taste in the wine due to the heating oxidation and improper storage is called what? So basically they are asking browning happened in wine during heating. And what is the name of that reaction? Maillard reaction, Maillerization, caramelization, and ascorbic browning. We know all this thing except the second option. See, in exam we cannot study every single thing. This is one of such example of that question. But you know what is a Maillard reaction, okay, and you know what is a caramelization, and you know what is an ascorbic acid browning. You don't know the option 2. So this word brownish red color alter the taste in the wine due to heating. Is it a Maillard reaction, caramelization, or ascorbic acid? First thing is brownish red color and altered taste definitely is not ascorbic acid browning. Okay, so they haven't told any other points. So, and we also know what is the caramelization. Okay, and this is also not a Maillard reaction because there is no involvement of any other amino acids. So the only the options which you can think of is Maillerization. So that's how you need to compare the answers with the question sometimes, because obviously you cannot study each and every terms like this in the books, because some books might have this point, some book might not have this point. But if you have understood the concept, you can derive an answer within the question. Okay, so that's it. Thank you for watching this video. Please like and subscribe and share our YouTube channel with your friends if they are studying for any food related examinations. Join our Telegram community. The link is given in the description, and the PDF of this specific video is also given in our Telegram channel. You can download the PDF and study yourself. And if you are studying for descriptive paper, just like how whatever I have discussed in the video, just revise it once and you can write it as a content. Okay, thank you, and let's meet in the next video.